Looking at a traditional emergency medical services helicopter, like this ADAC Luftrettung AC-135, reveals a machine defined by mechanical complexity. Flying an aircraft like this requires constant, simultaneous four-limb coordination. The pilot manages the cyclic stick for pitch and roll, the collective lever for vertical thrust, and the floor-mounted anti-torque pedals for yaw, actively adjusting all four to maintain aerodynamic stability. The VoloCity cockpit looks different. There is no collective lever. There are no floor pedals. The panels are clear of the dense rows of circuit breakers and toggles found in legacy airframes, leaving an empty floor space and a minimalist side-by-side seating arrangement. This architecture is the direct result of a specific engineering protocol known as Simplified Vehicle Operations, or SVO. The VoloCity eliminates mechanical linkages from the flight control loop entirely. This requires a new tactile and psychological relationship between the pilot and the machine. To understand how this empty cockpit functions, we first have to look at the physical forces lifting the vehicle. The VoloCity utilizes a propulsion architecture known as distributed electric propulsion. It relies on an array of 18 independent electric propulsion units, or EPUs, all featuring strictly fixed-pitch aerodynamic blades. Because these blades have a fixed pitch, the aircraft cannot alter blade angles cyclically or collectively using mechanical swash plates, which is the mechanism traditional helicopters use to maneuver. Instead, the aircraft maneuvers by changing the RPM of each individual motor. Human reflexes and cognitive processing speeds are biologically incapable of manually balancing 18 independent thrust vectors simultaneously. Because human mechanics are too slow to maintain stability across 18 rotors, physical control is outsourced to microprocessors, leaving the pilot to issue high-level trajectory commands. Those trajectory commands are issued through the side stick inceptor, which serves as the sole physical conduit between the pilot's operational intent and the aircraft's path. The stick itself operates within tight physical constraints. It features a restricted mechanical throw of just 10 to 15 centimeters in any direction. This short throw means the pilot can command pitch and roll entirely through subtle wrist and forearm articulations, eliminating the need for gross shoulder movements or full arm extensions. This single stick also handles the missing floor pedals. The pilot commands yaw simply by twisting the ergonomic grip of the inceptor on its vertical axis. As the pilot moves the stick, they experience zero mechanical aerodynamic feedback from the outside air. The resistance felt in the hand is synthetic, provided by spring-centering mechanisms in the base. This creates a built-in safety mechanism. If the pilot releases their grip, those springs snap the stick back to a neutral zero detent. The flight computers recognize this neutral state and immediately execute an active hold algorithm to maintain a level, stationary hover. Consolidating spatial attitude control into the fine motor movements of a single hand minimizes the physical work of urban transit. This leaves one final axis of flight, vertical lift, which in legacy aircraft requires constant manual adjustment of a heavy collective lever. The VoloCity replaces the collective with an altitude thumb actuator, a spring-loaded vertical toggle integrated directly into the upper housing of the side stick. Pressing this actuator up or down does not physically throttle the motors. Instead, it issues a digital request to the flight computers for a specific vertical velocity rate, such as a climb at 500 feet per minute. Releasing the thumb switch locks the system onto barometric and radar altimeter data to hold a precise three-dimensional position in space, removing the need for continuous manual inputs to stay level. But how does the physical displacement of this side stick reach the motor inverters without steel cables or hydraulic lines? The VoloCity utilizes a military-grade fly-by-light architecture. The physical movements of the joystick are instantly transduced into binary optical pulses. This technology was chosen to counter a specific threat present in urban environments: electromagnetic interference. Traditional copper wiring can act as an antenna, absorbing radiation from cell towers and power lines, which can induce transient electrical currents. Photons traveling through heavily shielded fiber optic cables are not altered by external electromagnetic fields. Fly-by-light provides deterministic signal latency, ensuring the aircraft's control integrity is insulated from the invisible radiation of the city. Flight computers execute maneuvers purely through differential thrust. To command pitch and roll, they dynamically increase RPM on one sector while decreasing the opposite, physically tilting the disk. For yaw, computers increase clockwise rotor RPM while decreasing counterclockwise rotors, generating torque while keeping lift balanced. Managing this forward pitch along urban transit corridors introduces a specific challenge. Holding the spring-loaded side stick forward for long durations causes physical fatigue. To solve this, the Cockpit teaches a friction clutch, a mechanical lock on the side stick's forward pitch axis. Engaging this clutch locks the aircraft into an optimized 48-knot cruising speed, allowing the pilot to remove their hand from the primary controls. With their hand free, the pilot can operate the detented rotary dials on the center pedestal, ensuring accurate menu selection even when experiencing low-altitude thermal turbulence. The friction clutch enables a shift from active manual flying into an autonomous monitoring phase. Traditional helicopter emergencies rely on a highly precise manual maneuver known as auto-rotation to survive a catastrophic engine failure. In the VoloCity, the 18 rotors are strictly fixed pitch. They physically cannot be feathered to alter their aerodynamic drag, making traditional auto-rotation impossible. Instead, the aircraft is engineered to meet the EASA standard for fail operational redundancy. If a single motor fails in midair, onboard optical safety monitors detect the RPM drop in milliseconds. The flight control algorithm instantly reconfigures the thrust matrix, surging power to the remaining healthy rotors to compensate for the lost lift. During this emergency, the pilot is instructed to keep the joystick centered and continue making normal, gentle directional corrections. There are no emergency pedals or levers to manipulate. Surviving a mid-air component failure relies on instantaneous algorithmic asymmetric thrust compensation, removing the need for extreme human reflex. Outsession survival to algorithms introduces a critical vulnerability, the potential failure of the central flight control computers. The primary defense against this is a triple redundant primary computer array. Beyond that, a concept called dissimilar redundancy is employed. A fourth, air-gapped backup computer is built with different microchip architecture and coded in a different programming language to prevent fleet-wide software bugs. If the primary computers die, this dissimilar backup takes over the optical network. For the pilot, this digital failure requires zero physical intervention. When facing severe system degradation, such as a critical battery thermal warning, the pilot interacts with the Garmin G3X Glass Cockpit to select predefined contingency modes. By selecting touch labels like Land at Nearest Vertiport, the pilot can manage air traffic control and assess landing zones, while the automation calculates the safest energy route. The VoloCity is also prepared for highly improbable events, such as a total unrecoverable power loss across all 9 batteries, or catastrophic structural failure. For these scenarios, the aircraft integrates a full fuselage ballistic recovery system. This structural parachute is deployed via a guarded physical switch in the cockpit. Once activated, a solid propellant rocket fires upward, violently smashing through the composite skin and extracting a massive parachute canopy. This canopy forcefully arrests the free fall of the entire 1,000-kilogram airframe, lowering it safely to the ground. This physical tactility extends to other critical systems. The overhead fire suppression T-handles are strictly mechanical pull cables, and the center pedestal emergency stop button requires deliberate pressure. The VoloCity redefines aviation safety by decoupling the human hand from raw aerodynamics, relying instead on overlapping layers of optical data, automated microstability, and physical failsafes to manage the mission.